And as part of the sort of interdisciplinary setup of everything here at OSoMe, sorry, maybe a little Zoom pop up. We've organized the OSoMe Speakers virtual event. So the whole idea is that we're going to bring together some of the brightest researchers and scholars who are working to understand social media and its impact on the world and technology in general. So if you're interested in sort of the talks that we're having today, and I would imagine that you might be interested in those that we have lined up in the future as well. So you can find out more about that on the events page, which is linked there at the bottom of the slide. And with that, I'm going to introduce Luca.
I want to interrupt you real quick. For everybody who is in the room, because of the national emergency system testing that is going to be going on at some point in the next hour or two, could everyone who is in the room turn off your phone? Don't put it on silent, like your phone needs to be completely off, just so that way it doesn't accidentally go off during the talk.
It will make noise even if you have it on silent. That's the idea.
So before we get rolling.
Should do that as well.
All right, Sarah.
Okay, sorry. So it is my pleasure to introduce Dr. Luca Luceri. Luceri is a research scientist at the University of Southern California's Information Sciences Institute. He's a co-PI of two major research programs that are working on techniques to detect, characterize, and track geopolitical influence campaigns, as well as develop network models to simulate the effects of moderation policies to combat online harms. His research interests fall in the areas of computational social science, AI for social good, and behavioral science work. Generally speaking, his research leverages AI, machine learning, data science, and network science to detect, investigate, and mitigate online harms in socio-technical systems. And today, as you can see, he's going to be talking about sort of using AI to counter influence campaigns. With that, please, now we have some hands.
Thank you, Matt. It's a big honor for me to be here and see in person these people I've been working with these few months and years. As you said, I'm gonna discuss my past and current efforts to counter information operation on social media. I'll describe some of the methodologies that I designed using a combination of machine learning and network science techniques to detecting, modeling, and mitigating online harms. Technical system. But first of all, let's try to understand what is information operation, and the illustration in this slide will help me with that, will help me also going through the outline of this talk. And this illustration here mirrors the life cycle of an influence campaign, where initiators or instigators create inauthentic personas to generate and share content on social media networks. And the drivers of influence campaigns can be of different nature, ranging from fully automated accounts, like bots, to human operators, and of course their combination thereof. And in the first part of this talk, I'm going to discuss and focus on inauthentic state-sponsored human operators, also known as trolls. And I'll present an approach based on reinforcement learning that tries to extract behavioral cues that enable their detection. Inauthentic personas like trolls generate and disseminate content on these platforms and use a variety of techniques to amplify content, to create an illusion of consensus, and manipulate platforms' feed. So in the second part of this talk, I'll present my ongoing effort to detect these inauthentic coordinated activity through a variety of network-based approaches. The main issue of these coordinated campaigns is their downstream effect on people and organic users that are susceptible to these influence efforts. And these users become, in turn, unwitting collaborators of this campaign. And they do that by further resharing, amplifying content generated by these inauthentic users, which can eventually be picked up by mass media and news outlets, and so resonate to a larger extent. So in the third part of this talk, I'll provide an overview of my vision on what we can do to mitigate these harms and influence attempts. and in particular, trying to protect those that are more susceptible to these attacks. So this talk connects the dots among these three main research directions. First, how can we detect inauthentic influence operators? Second, how we can identify signals of coordination that can enable the detection of influence campaigns. And finally, how we can mitigate these online harms. So in the first part of the talk, I'll present you a methodology that I designed during my PhD to detect inauthentic personas by adapting and mapping this task to a reinforcement learning problem. So as I briefly mentioned before, the social media landscape is populated by organic, genuine users and a variety of inauthentic personas. And among those, automated accounts, bots, also known as bots, received a large amount of interest and attention by the research community, which developed automated tools for their detection. I guess everybody here is aware of the most popular one. However, as time went by, researchers started realizing that other forms of abuse exist, not only leveraging automated accounts, but involving human operators like trolls. And I guess everybody here is again aware of Russian trolls and Russian interference and troll farm, Russian troll farm during the 2016 election. It's important to note here that we refer to troll to human operators that who are involved in influence campaigns and have a political agenda. Therefore, we do not consider any other trolling activities, internet trolling activities that might involve hateful or harmful behaviors. However, being humans, these inauthentic personas are much more challenging to model and detect than bots. Previous work found, for instance, that trolls shared content that resemble genuine activity, incorporating also general interest topic, and their behavior is not consistent over time. Therefore, their automated detection is not a straightforward task. Indeed, researchers found challenging to detect trolls when looking at sharing activities and features that were used to detect other inauthentic behaviors. Linguistic approaches work well in some specific scenarios, but they have generalization problems as they exploit patterns of English misuse, English language misuse of content and function words that are common to non-native English speakers, such as Russian trolls. And this is particularly important because, and given the diversity of information operation carried out around the globe, originating from different countries, targeting various states, various countries, and therefore using also different languages. Therefore, the idea that I had was of designing a language agnostic and content agnostic approach that will leverage only behavioral cues from social media users' activity. And in such a way, if linguistic cues are lost or we cannot have access to textual content anymore, we will still be able to uncover this inauthentic behavior. And in doing so, we sort of anticipated the use of technologies such as language models or ChatGPT for malicious purposes. And indeed, some papers that you might be aware of started providing initial evidence of the use of these technologies by inauthentic actors. And therefore, our ability to detect inauthentic accounts based only on linguistic cues might be hindered by the use of these technologies like. And especially because distinguishing between content generated by human actors and large language models is nowadays a challenge. And therefore, given that mimicking human behaviors is way more challenging than imitating language, this approach that I'm going to present you today offers some competitive advantages in the age of large language models over solutions that are based only on text. So I started looking at the behavior of trolls and organic users through their sharing activities. And the idea that I had was that organic user activity might be affected by their interaction with peers, and by the feedback they receive by other users. For instance, a user might be more motivated to share new content if they receive social approval or positive feedback from their peers, from other users. While a troll might not be. And the idea is that trolls have a political agenda and they perform their agenda regardless of the feedback they receive. And therefore, they are not driven by the feedback they receive, so they are driven by the objectives of this agenda. So the rationale of this method is that the incentives driving trolls and organic users might be different, might differ. But how can we operationalize this? How can we estimate these incentives? And the objective of inferring intent and motivation from an observed behavior has been studied in the context of a framework called inverse reinforcement learning. And given that inverse reinforcement learning goal is exactly to extract the rewards or incentives behind an observed behavior, I had the idea of mapping our troll detection problem to an inverse reinforcement learning task. So to do so, I had to frame our social media users as reinforcement learning agents. And in reinforcement learning, agents learn how to achieve a goal by performing a sequence of actions in a certain environment. And the agent optimizes the action to perform based on some rewards or penalties. And the environment is framed as a Markov decision process that includes, but is not limited to, a set of states which represents the situation the agent finds itself in the environment, a set of actions that the agent can perform in the environment, and a set of scalar rewards that are associated with each transition from one state to the other when performing a given action. And the sequence of visited states and performed actions compose a sequence that is called trajectory, zeta. Now, while in reinforcement learning, the agent is provided with a reward function that is used to achieve the goal and optimize a policy, the rationale of inverse reinforcement learning is to find these rewards, to find the rewards that might explain an observed behavior. And again, the observed behavior in our scenario is the sequence of state action pairs. So it's the sequence zeta. Formally, the aim of inverse reinforcement learning is to find a hidden reward function that maps each state action pair to a scalar reward. Now,
the assumption that the agents are trying to maximize reward, as in standard reinforcement.
Yeah, exactly. The assumption is right. There's some literature where new development of approaches in inverse reinforcement learning where they assume that the behavior is not the optimal. The observed behavior might not be the optimal one. So they adjust parameters to take this into account. The behavior might not be optimal. So now the main challenge here is how do we map this formulation to our scenario? How can we frame Twitter users as reinforcement learning agents, and how can we frame Twitter as our environment? And the intuition was to look at the possible engagement and interaction on Twitter, where a user can perform or can receive, and map this interaction to states and actions. So starting from the actions can be every sharing activity that the user can perform. Here I started from the most used ones, but this can be further expanded to other actions or different granularities, like you can have positive replies, negative replies, and include some other facets like hashtags or URLs and so on and so forth. So here I started from these four that are sharing an original content, retweeting, resharing, replying, and even posing or. And states represent the feedback received from the environment. So I envision this to be the potential interaction received by given users from others. And of course, this can be a received retweet, a received reply, or nothing, meaning that the user does not receive any engagement. So according to this formulation of Twitter users as reinforcement learning agents, I could build a sequence of chronologically sorted state action pairs for every users by leveraging their activity logs. And the inverse reinforcement learning framework takes as an input the sequence of the user and returns as an output a set of scalar rewards. And given that we have a combination of 3 possible states and 4 possible actions, we have 12 possible rewards. And here is shown an example of a reward function depicted with a heat map, where each element represents a scalar reward associated to each state action pair. And we have done this for every Twitter account that we have at our disposal. But what to do with this reward function now? Well, we can use these reward values as features of a machine learning approach that aims to classify accounts as either organic users, as either an organic user or as a troll. And as a study case, we use the Russian trolls involved interference during the 2016 election. And here are the results. So first of all, on the top right, we show the classification performance in terms of AUC with different off-the-shelf machine learning algorithms. And among these, AdaBoost achieves the best AUC, close to 39%. On the left side, we can see how the performance, the classification performance, improves when using longer sequences and accounts with longer sequences. While on the bottom, we compare our approach based on inverse reinforcement learning with a linguistic approach. And we can observe how we achieve performance that are comparable to a linguistic approach without considering at all the content, the textual content of tweets. And this, of course, represents, again, a competitive advantage in the age of large models, given that these technologies can produce, generate, and refine text. And in particular, our model is more conservative than the linguistic one, achieving a higher precision, which represents a positive asset when it comes to moderating counts, content, banning, and suspending users. Another important characteristic of this model is that it allows us to interpret the features and capture some peculiar behavioral differences between trolls and user accounts. And in this figure, I will display the distribution of the rewards that are estimated by the inverse reinforcement learning framework of the 2 different classes of accounts. The x-axis represent the state action pairs, the different state action pairs. while the y-axis is the estimate. And the higher the reward, the higher is the motivation or the incentive in doing a certain action when the user is in a given state. And here we can observe some interesting differences. First of all, it can be noted how, on average, trolls have higher rewards for sharing a new original piece of that is represented by the action TW in this spot. And they share original content regardless of their state, which might suggest that trolls perform their sharing activity regardless of the feedback received by the other users, which makes sense and confirm our intuition about trolls' agenda and their objectives. On the other hand, users appear to be more rewarded than trolls when their content is reshared by others. And given that retweet represent a form of social approval and is often associated to social endorsement, this might suggest that users are more susceptible to social approval than trolls. Again, this was probably expected, and this was our initial intuition, but we mathematically proved and modeled this by using this inverse reinforcement learning framework. So overall, our results show how inverse reinforcement learning may represent a useful addition to the toolbox of user behavior analysis. I've shown how it can be used to model human decision making, and the rewards estimated by this model can provide can shed light on behavioral differences between different classes of accounts. And this idea was advanced and validated in the context of different information operations originating from different countries in an article that has been recently accepted for publication in Science. Will be out soon. Should I share with you?
I can send it around here.
Okay, so moving forward, we figured out how these users are becoming increasingly sophisticated and are inclined to act in a coordinated fashion. Therefore, in this second part of the talk, I will present some of our current efforts to identify these coordinated actions used in influence campaigns. So our previous works already showed how influence campaigns are rarely the work of a single individual, but are complex and coordinated efforts carried out by authentic personas in concert. And these coordinated efforts might sometimes have the objective of pushing content, making it more popular than it is, as we discovered in the context of COVID-19 disinformation campaigns, where inauthentic personas were artificially amplifying content of disinformation actors. Here, disinformation does an example, and they were doing this in a coordinated fashion. Or even what we observed in the context of the 2020 US election, when clusters of users were involved in copy-paste activities, sharing similar tweets with small variations, with small nuances, to create an illusion of public consensus. And we discovered that most of these users were also involved in pushing fringe and conspiracy hashtags in a coordinated way in the attempt of manipulating the feed ranking algorithm. So how can we identify these coordinated actions, given that these personas are becoming increasingly sophisticated? And the idea here is to detecting tactics of influence coordination by pinpointing exceptional or unexpected similarities in their sharing activities. And the main assumption, of course, is that the genuine users are independent. They should be independent from each other. They should act independently from each other. And these similarities can encompass different behavioral traces, ranging from common sharing activities, for instance, resharing similar tweets, sharing similar links or hashtags, or having temporal and linguistic similarities in the sharing activities, or behaviors that resemble automation, like frequently, repeatedly resharing content in a rapid way. And these behavioral traces are often used to construct build similarity graphs that portray user similarities using edge weights. So the similarity is represented by the weight of the edge. And to detect accounts involved in orchestrated influence campaigns, existing solutions strategically filter out edges with low weight by setting a high similarity threshold. The underlying assumption is that connection between highly similar users can reveal coordinated clusters of accounts that are likely to be engaged in information campaigns. To be noted here is that users that are not linked to anybody else after this filtering are not considered to be coordinated. So our question is edge filtering the best strategy? And this slide shows an example of how a similarity graph looks like. We consider this is just an example of an information campaign from Iran, where the driver of this information operation are depicted in blue, while organic users in orange. And when filtering out low weight edges, we can notice how both groups persist, despite their size in terms of nodes and edges is reduced. And if a more aggressive filtering is performed, both groups appear to disrupt, which is good news when it comes to orange nodes, users, but it's not a positive signal for what pertains to blue nodes, as these are the accounts that we want to identify. Also, we still see some orange nodes, some orange groups, which represent false positives in this scenario. So this experiment gave me the idea to look at some other properties of the similarity graph. And by looking at this example, I noted that the drivers of this campaign tend to sit in the central position of the network. Therefore, the idea that I had was that we might exploit some other topological and structural properties of this network. If I'm drinking, it was yesterday pizza that I wanted to skip. So I started investigating whether node centralities can provide signals to identify coordinated data. But in a second research question, I also wanted to understand if the network topology, and in particular, the network representation of this similarity graph, could be used for prediction purposes. And to this aim, I guess you already know this data set, but we leverage the Information Operation Archive, which consists of over 100 information campaigns originating from more than 20 countries. And in this work, we focus our analysis on the campaigns listed in this table because of their significant scale in terms of larger user base with respect. So starting from the first research question, we begin by looking at node centralities and their potential efficacy in coordinating, in detecting coordinated. And so with this example, I started evaluating the impact of filtering out nodes based on their eigenvector centrality. We tested this with different other centrality measures, but eigenvector discriminative power. As we can see here, by removing nodes with low centralities, we are able to filter out the organic users, the orange nodes, while maintaining a big portion of the blue component, our coordinated group. Now, this example, this initial assessment was followed with evaluation, where I compare the results between edge filtering and node pruning, the two different strategies, for every similarity network. That are built based on the behavioral trace that you can see on the y-axis. The x-axis shows the various influence campaigns there. And the color map will represent the improvement of pruning nodes against filtering edges. So results show that the approach based on node pruning significantly enhanced the precision of the classification while maintaining the same recall on average. And precision of node pruning is 42% higher than edge filtering. And this holds true across, this improvement holds true across different campaigns and different similarity graph, except for a few combinations. However, when we looked at the, I think I need to specify here, for both methods, we optimized the threshold to run a fair comparison. So we use the best threshold for both node pruning and edge filtering. However, when looking at the performance of our approach for each single similarity graph, we realized that a unique behavioral trace cannot accurately capture all these coordinated campaigns. So the intuition then was that we could combine all these similarity graphs in a unique similarity network that connects two nodes if they are connected in at least one of the similarity graphs. And then node pruning is applied as before, based on eigenvectors. So results seems to confirm our intuition. First of all, let's see, we can observe that different techniques are used across different campaigns. I said before, for example, if we look at China, Russia, and Venezuela, the co-URL similarity graph is the best one, but it's not the case for Cuba and Iran. It does not work very well for Iran. While co-retweet and text similarity seem to be the behavioral traces that better differentiates these two classes of accounts in the second observation is that fusing multiple signals can allow us to get the same performance of the best behavioral trace without knowing that in advance which is the similarity graph that more accurately capture the coordinated groups. It should be noted that fusing network does not improve the performance, but allows generalizability across campaigns. All but Egypt, where the fast retweet similarity graph seems to interfere negatively with the other signals. Therefore, we are trying to understand if it's better to remove, pick the fast retweet out of this formation. So overall, where we can apply this methodology, first of all, when the ground truth is not accessible, therefore, information operation can give us an understanding of how to tune the parameters. We can have conservative model using a high threshold that gives us high precision. And of course, fusing is the best strategy when it comes to a generalizable model across campaigns. Moving forward, I also extended this idea of fusing networks and using multiple behavioral traces to test whether these the network structure of this similarity graph can be used for predictive task. And the idea is to use graph embeddings to identify information operations in more challenging scenarios. For instance, when different campaigns interact with each other, or to predict future campaigns. In this slide, I show the graph embeddings of the fused similarity network for the 6 information campaigns by using a TSNE, a low dimensionality reduction based on TSNE. And from this figure, it appears that this idea has potential, and indeed we can see how the two classes of accounts are often well separated. And here are the classification results. We're using a random forest trained with these node embeddings, evaluated with a 5-fold cross-validation. Once again, we observe how a unique trace is not enough and cannot capture accurately coordinated accounts. Retweet works well in one campaign, co-URL works well in another one. And fusing allows us to achieve better classification performance in all the campaigns in terms of both AUC and F1 score. And most importantly, once again, we can build a very conservative model. Also here, the precision is pretty high, very close to 100% in all the campaigns, but on average, around 96%. In a more challenging scenario, we try to consider the interaction across different campaigns and also their similarities. We thereby created a unique embedding by looking at a unique fused similarity network. And here is visualized by using a TSNE for the dimensionality reduction. We should take into account that here organic cues are not visualized, just to minimize visual clutter, but of course in the classification task they are. But before moving to the classification task, it's worth noting two things. Most of the users are separated based on their country, particularly evident for China, Iran, Egypt, and Russia. But there's a cluster in the middle that incorporates users from different information campaigns, from different countries, that might suggest that there's some interstate interaction and coordination. And we are working with the IU team to understand more about this and potential coordination across different states. Some preliminary work from another research group started confirming this intuition, but so going back to our classification task, we evaluated this approach in this challenging scenario where a unique embedding space is built. And results also in this scenario seem to be promising, reflect the high precision once again, as can be seen in stable. We achieve an F1 slightly lower than before. This is because still we are close to 80% of F1 and 92% of. Finally, last experiment, we try to evaluate our approach in a predictive task. The idea is to classify the users that will be involved in an information operation after a specific year based on the users active in the previous years. So for instance, given all the users active in 2010, we aim to classify all the users active from 2011 onwards. Or given all the users active in 2010 and 11, we aim to classify users that are active from 2012 onwards, and so on and so forth. And we can notice, of course, how the classification improves with time and with more available information. However, our approach still always have a very high precision and achieve an F1, and then you see of 0.7 and 0.8 in 2017 and 2018, respectively, which is a particularly relevant result given that a high fraction of malicious accounts became active in 2018 and 19. So to summarize, this approach is giving us very high precision, is building a very conservative model. It can be used when a portion of nodes are labeled, so it can be used in a supervised fashion. Therefore, we need count to be partially available. It looks promising also in challenging scenario, predictive scenario, and in scenarios where we have interacting campaigns. Probably coordinated. This is a work that will expand in the near future. So moving to the final part, I will be quick, but I want to provide an overview of my vision and future work to mitigate this harm. And in doing so, I'll show how the models that I presented you today can inform the intervention strategies that we aim to design to mitigate this harm, but also in particular to protect the most susceptible audiences. So we discussed how influence campaign employ inauthentic actors and coordinated behaviors to manipulate online platforms. And unfortunately, users who are susceptible to these deceptive activity might engage with these inauthentic personas and reshare content generated by these accounts. Therefore, they become unwitting collaborators and contributors of these influence efforts, further amplifying their activity. So how can we mitigate this? How can we minimize the harm for the most susceptible users to this? Well, we can propose different intervention strategies that might range from very aggressive strategies, including banning the accounts, removing content, but also to more moderate actions like reducing the exposure to problematic content or nudging the use. And this idea led to a project funded by the Swiss National Science Foundation, which is called Charisma. Whose objective is to create a computational framework that evaluates the impact of different moderation strategies. And it does that, we're doing that through agent-based modeling, where we plan to evaluate in a controlled environment a variety of policy instruments, which might allow us to have a principal understanding of the intended and unintended consequences of regulation. And these models can be informed by the work I presented today, and I envision 3 steps. In the first step, we can bake in the simulated models some of the behavioral traces and coordinated actions that I showed you before for replicating authentic behaviors. For example, based on exceptionally similar activity, story sharing or sharing new content, we can model interaction and accounts. We can replicate tweets or generate tweets by using large language models, also trying to replicate the small variations in the tweets these coordinated accounts share. But also we can also incorporate typical behaviors of these state-sponsored actors by modeling their incentives using the inverse reinforcement learning framework that I showed you before. For example, based on the estimated rewards that we estimated with Russian trolls or with other actors, we can train these agents to emulate their behavior that will be driven by the incentives. And while the first step focuses on bad actors, the second step, we can model authentic users. And similarly to bad actors, we can model the users' decision-making with the inverse reinforcement learning framework, leveraging the incentives that we estimated with the organic users. What we can study, and will be particularly interesting to connect, is the susceptibility to influence or to misinformation of the users with their incentives. For instance, leveraging previous works on human-bot interaction, we can also consider the characteristics of the interplay between human and bots, and incorporating some of the characteristics, such as demographics, psychographics, political leaning, or the ideology of these users. I will not go into the details of these, but of course, we have a huge body of literature around susceptibility to influence, misinformation, and the signals that might be included. So through these two steps, we can simulate the interplay between coordinated influence actors and organic users. And of course, we can do this in a variety of contexts. For instance, we can include cross-posting activities from other platforms. Videos shared on Twitter, from TikTok. And therefore, we can incorporate in these models the dynamics and interaction between content originating from the same platform or different platforms. And we can, and the objective will be, again, to understand how to mitigate harm. And indeed, finally, in step 3, we can evaluate the impact of different moderation strategies to harm this coordinated activity. And the idea here can be to propose personalized and tailored intervention to protect the most susceptible users. So we can take, for instance, an example about conspiratorial YouTube video shared on Twitter, but this will be applied to many different scenarios. Just for the sake of this illustration, I'll show an example with the YouTube video. And I'll show this example taken from the paper of Phil, where we can see in this network that when susceptible users are exposed to influence actor and to the content they share, the spread of misinformative video is quite high because the susceptible users adopt this content, which is represented here by the idea here with this project is to simulate the enactment of a given moderation policy to reduce the spread and adoption of this program. For instance, one might think of removing the content, or nudging the users, or reducing the exposure. And these and many other policy instruments will be tested in this project, which started a few months ago and will be carried out in collaboration with IU and colleagues from Switzerland, from SUPSI and University of Zurich, including media and internet governance researchers that will are informing our models to evaluate a wide range of instruments. And that's all. Everything you have seen today is the work of work done in collaboration with many amazing students, collaborators and mentors that I had the privilege to work with during the last few years.
Well, thank you for a very interesting talk. I think we can start to take questions now. The first thing I'll say, Luca mentioned maybe we can try to give a little priority to folks who are on Zoom because the Zoom will end and then we can hang out and stay longer. So if you do have questions on Zoom, please feel free to drop them. Caitlin, I'm going to look on you to manage if you don't mind. I'm not in the Zoom room right now. But I don't think anybody has put anything in just yet. So if anyone in the room has something, we can get started. Rachel?
Oh, cool. Yeah, super cool presentation. I love the slides and stuff. So about your inverse reinforcement learning framework, I'm just wondering, I mean, I know it doesn't depend on textual cues, it just depends on behavior. So I'm just wondering, what's the unique benefit of using rewards? Why can't you just probably use the temporal signal like retweet, nothing, like the block framework, which Alex worked on, as features of the users instead of plotting the rewards? So when you compare it, also like when you compare it against the linguistic,
Yeah.
you could have compared it, I mean.
Oh yeah, I could have compared it with block, but this was before block.
Oh, okay. Sorry.
This was work on,
Okay.
should they be?
Okay, sorry.
Yeah, no, it makes sense.
Okay, all right, sorry, man. Missed the temporal.
No, yeah. That makes sense, yeah.
Okay, so you
The
could,
the comparison should, should be done with block and we have also this other approach based on this Markov decision process modeling that takes the sequence and input the sequence to a large an LSTM and yeah. It takes the sequence, it inputs the sequence to an LSTM and classify the sequence as either belonging to a troll or a user. And then based on these classified sequences, it gives you a score and then use the score to classify the accounts.
yeah,
This was the paper I mentioned before that has been accepted in science. I can share with you and unfortunately it was concurrent with the block, so we don't have the
no, that's okay, no,
performance comparison, but this can be done in the future.
so is there any benefit of this versus using the reinforcement?
It works better.
This works better,
This works better.
Okay.
LSTM Pro is more powerful, but this is informed by the inverse reinforcement learning. So the modeling of the sequence is based on the inverse reinforcement learning framework. So we have the sequence of state action pairs, which is what we need for the inverse reinforcement learning. But this sequence, instead of being injected in the inverse reinforcement learning framework, is injected in LSTM. So the modeling is somehow similar. It's just that the inverse reinforcement learning estimates the rewards,
yeah,
and here we classify the trajectory.
yeah, so that's what I was wondering, where is there any unique benefit to estimating the rewards, like?
The benefit of estimating the reward is that the rewards are interpretable. It can give us an understanding of the differences in behaviors between trolls and users. With the LSTM, we try to explain the classification results using some framework of extendable AI, but we didn't get any informative features based on their sequence. So the benefit is that the inverse reinforcement learning allows us to have interpretable features, while this one works better, like the classification of this model. I should have the comparison here. You can see that is definitely more capable of classifying users. The drawback is the
Yeah, but that's that, yeah. Thank you, cool.
You manage the floor while you're here. I don't think anybody said anything on Zoom yet.
Sorry, this is just a follow-up. So in theory, LSTM could be also learning about the rewards, right? It has the same information as that.
yeah.
And related to that, how does the IRL framework estimates the rewards? If you said it, I missed.
I didn't go
Yeah.
deep into the math of this. The main idea is that it's a maximum likelihood estimation
Okay,
in
that's-
general. Okay.
That's good enough.
There are other approaches that we use that try also to use deep learning to infer the rewards, or they also try to maximize the entropy between the estimated trajectories, the estimated sequences. But the main assumption is to,
Okay.
based on the observed behavior, you want to driven by these treatments.
Thank you. I have more, but I'll let. Wow, that's a question. I can.
Yeah, so this is about the uncovering recognize work. You mentioned that it could be so the node pruning and the edge filtering can be used in a unsupervised setting. Then how do you decide the optimal threshold as the results are so different across scenario?
So let me start from this one. In this one, we just wanted to compare the two approaches. So we took the best threshold based on a metric. Here it's based on one. These experiments with many other metrics. And so we simply wanted to compare the two approaches. So we took the optimum based on all the samples that we had. Then when it comes to this one, when we wanted to see how this works, we optimized the threshold by taking out, by training the model by trying to optimize the threshold of a training set. The training set to optimize the threshold, if I remember well, was 2/3 and 1/3.
So that is in the supervised.
Yeah.
How would you do it?
We can, as done in previous works when edge filtering is used, you can take a conservative approach, and you take the 90 or 95 percentile to figure out the nodes. And actually, something that I didn't mention is when it goes to the fused model and you plot the performance as a function of the percentile, all the metrics and all the campaigns seem to work well with the 95 percentile. So based on this knowledge, in the future, I would use that threshold for other unseen campaigns.
And how do you get the embedding?
It was node to back. Yeah.
To back based on what network?
The similarity network. Each single similarity network.
Thank you.
Here I visualize the fused one, all the network were combined. But we have done that also, single similarity network.
Awesome presentation. How do you create these similarities? Like, you have a vector of co-occurrences of retreats, and you look
Similarly to all the work that in the past, bipartite graph weighted with TF-IDF, projected similarity network.
the question. You had the Iran, the InfoOps data sets. So I know we are working on that. That's why I'm asking. But so Twitter released 7 of these Iran data sets.
Yeah.
Which one was that?
We merge all the campaigns from the same country. First, because we noticed that actors interacted with each other across campaigns, and second, we wanted to be testing this in a more realistic scenario where topics were different and users were covering other topics beyond this, and we want more noise. More noise, and also in a more practical term, we wanted to see the results. We wanted to see these networks, and with like 100 or many campaigns we had.
I think one more maybe, and then I think we're over time, so I don't know if people are still Zoom, but let's maybe do one more, and then what's the fight for it? This kid goes.
I have more time. Go ahead.
So regarding LLMs as agents, have you tried playing around by making them agents and stuff?
No, we haven't tried making them agents, but we try to see if the LLM can first use to classify tweets as either belonging to a campaign or not. It's giving mixed results. Sometimes we are very.
This is ChatGPT.
We are trying different open source LLMs like Llama, Falcon.
Okay. But you're
we
not.
tried also ChatGPT. The problem was not the problem. The idea was to compare also the
Yeah. And you don't have. So our concern, most of us have this concern over here, is when you're using LLMs to mimic them as agents like this, because most of these are political tweets in some sense. It usually refuses to mimic that agent. So do you have ideas to tackle that?
It's a good point. I mean, if we want to go in that direction about politics, we should take this into account. This second part, this last part was probably not entirely focused on politics, but of course it's one of the main study scenarios.
Thanks.
Wonderful, thanks, everybody, give another round of applause. Goodbye, everybody on Zoom, thank you for joining. And we're gonna, I guess, find out how to end this if I can do it. Everybody, thanks for joining.
I have